How's it going, guys? Today I'm doing the Physics Honors Semester 2 Final Exam Review Packet. And the way I'm going to do this, I'm going to group every single section into these subsections. So this is going to be energy plus work, and this is question 1 of energy plus work. And I'm going to just make a video on the entire section, so questions 1 through 7, I'll try to explain. And I likely won't be able to draw a diagram, because I personally am also running out of time. I have to cram for different assignments and stuff. So question number 1 in energy plus work. A 4 kilogram ball is shot straight up. It goes 20 meters high. What was the initial speed of the ball? It's a very simple question. You're given the mass, 4 kilograms. You're given the height, 20 meters. And we need to find the initial speed. So we're trying to look for velocity question mark. So how can we do this? We have n, we have h, and let's see what equation we can plug these into with our givens, right? We can plug it into potential energy is equal to mgh, so we can do PE is equal to 4 times 9.8 times 20. And excuse any background noise. And that gives me potential energy of 784 joules. Now, of course, potential energy is equal to kinetic energy at the peak of an object's, if you throw an object in the air at its peak, potential energy is equal to kinetic energy. So we're going to plug that into the kinetic energy equation, 1/2 m, which is, 4, then v, which is, we don't know what v is, and that's what we're solving for, v squared. So we're going to do 784 times 2 divided by 4, square root of v, and we get v is equal to 19.80 meters a second. So that's how you do number 1. Move on to number 2. As I said, I'm going to be doing a bit quicker. So, you might have to pause at some bits. How much work is done on the ball to get it to 20 meters? So, in this equation, basically, the total energy of the entire system is the same as the work. So the total energy of the entire system, if I could remind you, is 784. And this is 1b actually, not number 2. This is 1b. 1a, the answer was 19.80 meters a second. So for 1b, the answer is simply 784 joules. Because work is equal to kinetic energy and slash potential energy in this problem. They're all equal to each other at the moment. Now let's move on to number 2. Assuming no friction, how high will the ball travel up the hill in the diagram below? So in the diagram, I have this, did that say a 3 kilogram ball? I think that's a 5 kilogram ball. There's like a hole punch right through it, so I can't really tell. But I think that's 5 kilogram ball. It's moving at 5 meters a second, and it's on top of a 5 meter high hill. So, let me just draw down quickly. 5 meters, well, 5 kg, it's moving at 5 meters a second. Very consistent. And now we're trying to see how high will it go up how high can it go up the next hill, right? How high can the ball travel? So there's 2 different forces that are acting on it. Right now it has potential energy and it has kinetic energy because it's in motion. So we have to calculate both of those, add them up, and then we have to plug it back into the potential energy equation. So let's do that. Kinetic energy is equal to 1/2 m, which is 5, v, which is 5, squared. Potential energy is equal to m, which is 5, 9.8, which is gravity, height, 5. And let me check real quick. There you go. So let's plug this in now. The kinetic energy is 62.5 joules. This is 245 joules. Now 245 plus 62.5 is 307.5 joules. The reason we're adding them is because it has both kinetic and potential energy, and we want to see how high can it possibly go which is total energy. So we're going to plug this number into the PE is equal to mgh equation. We'll do 307.5 is equal to mass, which is 5, gravity, which is 9.8, and then height, we're going to leave unknown. Divided by 5, divided by 9.8, and our height is equal to 6.28 meters. Oops, I'm covering it a little bit. This is the answer for number 2. Let's move on to number 3 now. Force of 50 newtons is needed to pull a bowstring back 0.50 meters. What is the work done on the bowstring? So the work equation is force times distance. Force for this is 50. D is equal to 0.50. So we just simply multiply those out. 50 times 0.50 equal to work. Work equal to force times distance over there. And I get work is equal to 25 joules. Okay, that's how you do number 3A. You should probably write that down, number 3A. Now let's look at number 3B now. 3B. At what speed does the 0.20 kilogram arrow leave the bow? So we know our work is 25 joules from part A. So considering that, we know that work is equal to kinetic energy, and at least when it is at the top of its throw arc, at the top of its arc, I guess you could say that. So we know we can just plug that in to the kinetic energy equation. 25 is equal to 1/2 m, which is 0.20, and we don't know what v is. So we're going to do 25 times 2 divided by 0.20, and square root of that. We're going to get v is equal to 15.81 meters a second. And that's the answer for 3B. Question number 4. Find the kinetic energy, potential energy, total energy, and velocities at points A, B, and C. Now this is going to be difficult to do without the diagram. Okay, I'm going to cut back because I have to leave in a few minutes, so I'm going to cut back, and then we're going to start number 4. How's it going? So let's continue with question number 4, and the velocity is 0 meters per second, the mass is 100 kg, and we have the height as well. Height is 15 meters. So to find we need to find from point A, the kinetic energy, the potential energy, and the total energy of the system. Now, since the velocity is 0, the kinetic energy of the system has to be 0. Because the energy, kinetic energy is how much energy something has when it is in motion. This car, at the moment, is not in motion, which means it has 0 joules of kinetic energy. You can automatically just write that off. And one thing to notice is that the total energy for the system will remain constant because energy cannot be created or destroyed. So now let's try to figure out the potential energy. The potential energy, we have, do we have the mass? Do we have the height? Yes. If the mass is 100, we have the height is 15, and we already know what gravity is. We're assuming this is on Earth. So the mass is going to be 100. Excuse any background noise. 100 times 9.8 times 15. 14,700. 14,700 joules. So to find the total energy, you add the kinetic energy and the potential. 0 plus 14,700 is 14,700. And we can automatically just put that number same for here as well. Because energy cannot be created or destroyed. The total energy for the entire system has to stay the same no matter what. And the velocity for the first section is 0 meters a second. It's given to us. Right, v is equal to 0. Now at B. Now at point B, the car is touching the ground, right? The car is at ground level, which means it does not have any more potential energy. Because potential energy is how much energy can it have based on its distance from the ground. So like this eraser has more potential energy at this point than at this point. If it was just on the ground like this, like this, right now it does not have any potential energy. So the car at the very bottom of the hill will have no potential energy. So we can automatically write 0 joules here. Now, I mean, if you think about this logically, you could easily just figure out that, hey, kinetic energy, if something plus 0 is equal to 14,700, that something has to be 14,700 joules, right? So basically, at the bottom of the hill, all the potential energy transfers into kinetic energy. That's what happens in a roller coaster. And now it wants us to find C. Hold on. Actually, let's find the velocity first for this. I'm going to erase this real quick. So we know that kinetic energy is 14,700. You can plug it into the KE is equal to 1/2 mv squared equation. M is 100. We don't know what V is. Squared. So we can try to find V that way. And the velocity is 17.15 meters a second. There you go. And now, point C is where the actual difficulties lie. So I mean, there's other ways to do this than the way I'm going to show you. You could calculate the point here, then you can calculate all the way down here, then you can calculate back up there. But what I'm going to show you is a different method. So you see you have this hill here, right? It's 10 meters. You have this hill before it at 5. What I'm going to do is I'm going to subtract the heights of this. I'm going to do 10 minus 5, which gives me 5 meters as my height. Right? And then I'm plugging this into the potential energy equation. The mass is 100, the G is 9.8, and the height is 5. This is because when this car goes up this hill, right, it's losing a certain amount of kinetic energy and replacing it with potential energy. Then when it comes back down the hill, the kinetic energy is restored, right? It has 100% kinetic energy at this point, which means that we can completely negate this entire hill. That's why I'm doing 10 minus 5. That's why I'm negating the hill. Right? So I'm going to do 100 times 9.8 times 5. And that's going to give me the potential energy. 4,900. So the potential energy is 4,900 joules. 4,900 joules. Now, we know that something plus 4,900 is equal to 14,700 joules. So you can do 14,700 minus 4,900 to get the kinetic energy, which is 9,800 joules. So now that we know our kinetic energy is 9,800 joules, and we can plug that into the KE equal to 1/2 mv squared equation. mv squared. So multiply by 2 divided by 100 square root, and we get our final velocity to be 14.0 meters a second. So that's how you do number 4. And let me erase all this now. And remember, you can pause at any moment. Like if that was going too quickly for you, you can pause, slow down a little bit. Number 5, a car rolls down a hill and smashes into a wall at the bottom. Describe the energy changes that take place. So, first you have a car, top of a hill, rolls down, and smacks right into a thick wall, right? I don't know why I made that a box. Okay, wall. There you go, smash into a wall. No, draw a little. That was like a border. It's fine. Object. So So the energy changes that take place. So as I've said before, at the top of a hill, the car only has potential energy. Because the car is rolling down the hill, it doesn't have a previous velocity behind it. So this car is v 0 meters a second. But what it does have is potential energy. So it has like the height of this hill, it has gravity, and then it has the mass of the actual ball itself. So what happens is to the energy is that the car starts off with only potential energy. Well, then what happens to it? As it reaches the bottom of the hill, all that potential energy is converted to kinetic energy. And once it reaches the bottom, there's no more potential energy left. So the car starts off with only potential energy, which is converted to kinetic energy. At the bottom of the hill. Now, after it goes to the bottom of the hill, the car stops after it hits the wall. So now, when that happens, the wall is absorbing all the car's energy, and the car is void of any potential or kinetic energy. So the car starts off with only potential energy, which is converted to kinetic energy at the bottom of the hill. Then the wall absorbs the car's car energy. The car's energy. Boom. And that's the explanation for number 5. Now, number 6 asks, what 2 things are needed for an object to have work done on it? You can look at the work equals force times distance equation. We know that work is equal to force times distance, so we need a force, and we need distance. So the car smashing into the wall, in the previous example, would not have done any work. Why? Because although the car moved a distance, the wall did not move any distance, which means the car did 0 work on the car, right? Now, what's important is, for work equals force times distance, that equation only works in the vertical system. It does not work horizontally. So, if a waiter, I forgot this guy, he's carrying, I don't know, a tray with glasses inside. Oh wow, those are horrible glasses. They look more like cupcakes. It's fine. If he's carrying like some stuff in his tray, and he moves horizontally with this tray in his hand, guess what? He's actually doing 0 joules of work, because work only occurs vertically. So the force, whatever the force is, has to be vertical. The distance traveled has to be vertical. Well, actually, the force doesn't necessarily have to be vertical, but the distance that the object has traveled has to be vertical. Which, most problems the force is also vertical. There's some exceptions though. So that's how you do number 6, that's the explanation. Let's move on to number 7. That's number 7. A 2 kilogram block is set on a horizontal table. One end of a spring is attached to the block and the other end is attached to a vertical support. The block is pulled back 0.5 meters from the spring's equilibrium position and released so that it oscillates horizontally. At the equilibrium position, and The velocity of the block is 2 meters a second. What is the spring constant K of the spring? Neglect the effects of the mass. Okay. So what we're first gonna do is we have the mass. Right, let's write down our given. We have our mass 2 kg. We have our x 0.5 meters. And we have the v 2.0 meters a second. So we're going to have to use the spring equation, right? F. We're going to have to use the spring equation for this question. So now let's see how we're going to do this. We're given mass, we're given x, and we're given v. So at the moment, we can use, because we're given mass and v, we have to think outside of our spring equations and also look at these other equations. So we have the kinetic energy equation. And that would be the first one I can use. I don't know where I'm going to go with this, right? I don't know like what direction I'm going to do or what I'm trying to solve. But what I do know is that right now I can plug m and v into the kinetic energy equation. So why don't we do it, right? K is equal to 1/2 2 squared. Let's say you do like a lot of things in math or physics or science. You just start plugging stuff in into equations that you know and see what comes out, right? Kinetic energy is equal to 4 joules. Now what can we do with that? So now that we have the kinetic energy we know is equal to 4 joules. So let's try to get, now if we know the kinetic energy is equal to 4 joules, and that is equal to the total energy of the system, then the potential energy of a spring, I don't know why there's not a P here, potential energy of a spring is 1/2 kx squared. So if I have 4 joules, so 4 over 4 is equal to 1/2 k x squared, 0.5 squared. I can solve for k, right? And again, kinetic energy of the system is equal to the total energy of the system at that moment. And the total energy of the system is the same as the spring being loaded. Right? So the total energy of the system has to stay the same. So the total energy of the system is 4. And after the spring is shot, it's kinetic energy, and when the spring is not shot, it's in potential energy. Well, that's the main difference there. So we're going to do 4 times 2 divided by 0.5 squared. Which is 32. So K is equal to 32 newtons over meters, or kilograms over seconds squared. Right? And this one I'd probably put newtons over meters, but remember that a spring K is a spring constant, and it can be in either newtons over meters or kilograms times seconds squared. So that's number 7, and I think that is the last problem of the energy plus work section of the final review guide. And that's how you do it.